Let's talk about setting up bounds for the double integrals after we've done changes of coordinates. We can do that, as we saw before, by substituting in new coordinates for old ones. In that example before, we saw that if we took our bounds in terms of x and y and substitute in our new variables, we can get a new expression for the boundaries of the region. And if we understand geometry, then maybe we can make our life a little bit easier. So for example, let's set up a double integral in polar coordinates to calculate the area of the region where 1 is less than or equal to x squared plus y squared is less than or equal to 2, and y is greater than or equal to root 3 times x. So we could go through and just plug at this and figure out exactly, what happens if I plug x and y into here. But let's draw this a little. Here, x squared plus y squared is greater than or equal to 1. That's the region that lies outside a circle of radius 1. And x squared plus y squared less than or equal to 2 is the region that lies inside a circle of radius square root 2. So we already know part of our boundaries in polar coordinates. Our boundaries in polar coordinates go between r equals 1 and r equals root 2. So we can write it that way. We could have gotten that by substituting in r cos theta for x and r sine theta for y, but if we can see that we're getting formulas for circles, then we're in good shape. The second constraint is y is greater than or equal to root 3 times x. So that's a line through the origin, and the line through the origin makes a particular angle, theta. So if we want y to be bigger than or equal to root 3x, it means that we're on this side of the line. And so how do we express that in terms of r and theta coordinates? Well, here we've got a particular theta coordinate, which is the lower bound, and then we go all the way over to this other theta coordinate, which is kind of the upper bound. So we want to figure out what those bounds are. So what's this angle? Well, if this line is y is equal to root 3 times x, then when x is equal to 1, y is equal to root 3. And so we get a triangle whose bottom is 1 and whose side is root 3. We know what that angle theta is supposed to be. That angle theta is 60 degrees. And 60 degrees is pi over 3. That's what our first part of this line is here. Our next part of that line is 180 degrees off from that. Theta is equal to 240 degrees. That's 4 pi over 3. So our double integral to calculate the area of this region would be a double integral of 1 usually in x and y coordinates, but in r and theta coordinates, it should be r d theta. 1 times r d theta. And then we're integrating r goes from 1 to square root 2, and we're integrating theta goes from pi over 3 to 4 pi over 3. So knowing the geometry here and expressing things in terms of angles makes our life a little bit easier, because if we just substitute in y is r cos theta and x is r sine theta, we could figure out what it is, but it would take us a little bit more work. When we're doing this substitution, we have to be a little bit more careful about our boundaries. We have to be careful that when we express our new region and old region in terms of each other, we don't accidentally double count things. We want to make sure that every point gets hit exactly once, with some allowance for the fact that the boundaries are allowed to overlap. So here's a little simpler integral. We're going to calculate the integral of x squared plus y squared dA over the circle of radius 2. To do this, we're going to turn it into polar coordinates. So we turn it into r d theta. X squared plus y squared turns into r squared. Now we have to figure out what our bounds are. Our bounds in r, to be in the circle of radius 2, we have to start at radius 0 and go out to 2. We don't want to accidentally do things twice by plugging in some negative radius or something like that. We only want to catch every point once. And similarly, because it's the circle of radius 2, I don't want to accidentally count the same angle multiple times. I only want to go, say, between angle 0 and 2 pi. I don't want to miss anything by accidentally going between like angle 0 and pi. I don't want to double count anything by accidentally going between pi and 17 pi or something like that. I only want to go around the circle once, and so I make sure that I just go between angles 0 and 2 pi. And there's a little bit of overlap there. Angle 0 and angle 2 pi are the same, but that's just happening on the boundary, and so that's okay. So this is the integral we get, and this one we can actually simplify. It's an integral from 0 to 2 pi of an integral from 0 to 2 of r cubed dr d theta, and that's going to turn into an integral from 0 to 2 pi of r to the 4th over 4 evaluated between 0 and 2 d theta. It's an integral from 0 to 2 pi of 16 divided by 4 is 4 d theta, and that's just going to be 8 pi. So the double integral in this case is eminently calculable, and we never had to integrate a square root. If we did this integral dx dy, we would be, integrating square root 6 ways from Sunday, and the first thing we'd have to do in integrating those square roots is we'd have to do a trig substitution. The trig substitution that we do would be remembering, hey, we should have been doing this in polar coordinates in the first place. Let's substitute it back into polar coordinates. So if that's the case, we might as well just do the double integral in polar coordinates right from the start. It makes our life drastically easier.